You know, when you hear the word maintenance, what pops into your head? Probably a mechanic working on a car, right? Or maybe someone changing a light bulb. But what if I told you it's actually one of the most complex, high-stakes fields in all of engineering? Seriously, it's this hidden science that keeps our entire world running. Planes in the air, factories humming, power flowing to your home. It's about time we looked under the hood. And when I say high stakes, I am not kidding. In the United States alone, industries spend over $300 billion a year on plant maintenance. Just to put that number in perspective, that's more than the entire GDP of a country like Finland. But here's the really crazy part. Experts estimate that about 80% of that cost is just wasted, thrown away fixing the same chronic failures over and over and over again.
So, that's the big question, right? Why does it cost so much to fix things? Well, the answer isn't really about the tools or the parts. It's about the philosophy. It's in the way we've learned to think about maintenance and how that thinking has evolved from just fixing stuff to becoming a sophisticated, data-driven science.
So let's start at the beginning with the most basic strategy of all. It's a philosophy most of us are probably guilty of in our own lives. If it ain't broke, don't fix it. But in the industrial world, this simple idea has a much more dangerous name. They call it the run-to-failure trap.
This is reactive maintenance. The idea is you run a machine, a system, whatever it is, until it completely dies. Only then do you step in and make the repairs. And look, it seems simple. In the short term, it even feels efficient, right? You're not spending money on something that seems to be working just fine. But this approach, it has some serious hidden costs.
So why is it a trap? Well, because almost all of your work becomes unplanned. It's just constant firefighting, running from one crisis to the next. That means your team is always in emergency mode instead of making smart improvements. To deal with the chaos, you have to keep these huge, expensive warehouses full of spare parts, just in case. But the biggest problem of all? You never learn anything. You never stop to figure out why things are failing, which means you're just doomed to fix the same problem forever.
Obviously, that kind of chaos couldn't last forever. This led to the first big evolution in maintenance thinking. People started asking, what if, instead of waiting for things to break, we could fix them before they do? This was the crucial shift from being reactive to being proactive, and it has a name: preventive maintenance.
The idea behind preventive maintenance, or PM, is actually pretty simple and familiar to all of us. It's like changing the oil in your car every 5,000 miles or going to the doctor for an annual checkup. The maintenance is scheduled based on time or usage. It doesn't matter what the machine's actual condition is. The whole goal is just to catch problems early and make the equipment last longer.
And a good PM program isn't just random guesswork. It's a highly structured process. Teams have to identify the most critical equipment, develop very specific tasks for it, figure out how often to do them, get everything scheduled, and then, and this is the most important part, they have to constantly evaluate if it's even working. It's a huge step up from the pure chaos of fighting firing.
But, you know, preventative maintenance has a flaw. You might end up fixing things that aren't even broken, which wastes money. Or even worse, you could miss something that's about to fail right before its next scheduled checkup. So engineers started asking a new question. What if we could actually listen to the machine and let it tell us when it needs help? This is the giant leap into what we call predictive maintenance.
Let's think about it this way. Preventive maintenance, that's your scheduled annual checkup with the doctor. But predictive maintenance, that's like wearing a fitness tracker that monitors your health 24/7. See the difference? It's not based on a calendar. It's based on real-time data about the actual condition of the equipment. You don't just fix things on a recurring basis. You fix them only when the data tells you a problem is on the way.
So how in the world do you listen to a machine? Well, you use technology that basically acts like human senses. Thermography uses infrared cameras to literally see hot spots in an electrical panel that signal a failure is coming. Vibration analysis can feel the tiniest imbalances in a giant motor that mean a bearing is about to burn out. And my favorite, lubricant analysis. It's basically a blood test for an engine. It can detect microscopic metal particles that show you exactly how things are wearing down on the inside.
Okay, so we've been talking a lot about machines and data and costs, but the stakes here are so much higher than that. A failure in maintenance isn't just about downtime or losing money. It's about quality, it's about safety, and sometimes it's about life and death.
This is one of the most sobering examples in modern history. When the Space Shuttle Challenger exploded back in 1986, it was, at its heart, a maintenance failure. Engineers knew the O-rings were a potential problem, But as the investigation later concluded, there was no quality maintenance program in place to actually track the increasing damage and find the root cause. It's a terrifying reminder that maintenance isn't just about efficiency, it's about responsibility. And that kind of brings us full circle. Even with all our modern technology, look at this chart. That 12% slice for emergency debugging, that's just a fancy new name for the same old run-to-failure trap we started with. It shows that despite all this progress, we're still spending a huge amount of our time just fighting fires. It just goes to show how hard it is to escape that reactive mindset.
So when you step back and look at all this, you see this incredible evolution. We've gone from just fixing things when they break to trying to prevent them from breaking, and now even predicting when they'll break. This whole journey has transformed maintenance from what used to be a simple chore into a genuine science.
This really recaps the whole story. We started with reactive maintenance, just fix it when it breaks. Then we got smarter and moved to preventive, fix it on a schedule before it breaks. Then we got really clever and moved to predictive, use data to fix it only when it's about to break. But the final step, where the science really takes over, is proactive. This isn't about predicting failure anymore. It's about doing a deep, root cause analysis to make sure that type of failure can never happen again. It's about fundamentally changing the system itself.
So here's the big takeaway. The ultimate goal of modern maintenance isn't just to get good at repairing things. It's about achieving reliability by design. It is a complete shift in thinking, away from just fixing problems and toward engineering those problems out of existence in the first place. It's about building a world that doesn't break.
And that leaves us with one final thought. Every single complex system you rely on every day, the car you drive, the elevator you ride, the power grid that lights your city, is operating under one of these maintenance strategies. It's this invisible framework holding our whole world together. So now that you can see it, ask yourself, what happens when the people in charge choose the wrong one?